Assalamualaikum and hi everyone. Now we are going to go deeper into applications of fundamental knowledge gained in chapter 2, 3 and 4 to understand the characteristics of semiconductor devices. We start with the simplest form of device, which is PN junction. But before that, let us refresh with the most important concepts from chapter 2, 3 and 4 that you really need to familiarize in order to understand the PN junction characteristics. In chapter 3, we have studied the carrier generation and recombination. But bear in mind that to understand the generation and recombination in chapter 3, we really need to understand the semiconductor fundamentals concepts in chapter 2. One of the most important things that you really need to understand is the formation of ionized acceptors and donors, which later is important to understand the formation of electric field in PN junction. You also need to really understand the concept of diffusion and drift current. What are the processes that induce the diffusion current and also the drift current? The basic of diffusion and drift current was introduced in chapter 3, but the formation of diffusion and drift currents in a material without applied bias was deeply discussed in chapter 4. The Fermi level concept and consistency at equilibrium also is very important to help you understand the PN junction. The objective of this video is to introduce you to the most basic knowledge of PN junction device. Let me introduce the general types of junction that we have in our devices. Junction in devices means the interface between two regions. For homojunctions, the regions are made of the same material but having different type of dopings. Heterojunction is the junction between two different types of semiconductor material. We also may have metal semiconductor junction and semiconductor insulator junction. The applications of the junctions are different depending on their types, and some of common examples are as written here. PN homojunction is made of a single crystal of one semiconductor material, usually silicon, that consists of a region with p-type doping and a region with n-type doping, separated at a specific boundary. The PN junction itself is a diode, which is a two-type terminal devices. The examples of diodes are as shown here. Some of you here may have learned about diode. Diodes can act as switches because it allows the current to flow only at one direction. For one polarity of the applied voltage, the current will flow, but for the opposite polarity, there is no current flow. The example characteristics is shown here, and this is the circuit symbol. Typically, a diode needs to be biased with 0.7 volts to turn it on, meaning to have current flowing through it. Let's see how the PN junction is created. To fabricate a PN junction, the common technique is to dope a region in a pre-doped semiconductor. In the example shown here, we dope a region in a p-type silicon substrate using n-type doping. Usually, the technique to dope the region is using implantation method, where we can precisely control the position, depth, and doping concentration. After doping, the material in figure A is created. To simplify things, for calculation and band diagram discussions, we cut the region at the A' line in figure A, and we will have figure B. Further, we cut along the B' line in figure B and tilt the figure 90 degrees. We will have a simplified PN junction schematic diagram in figure C. Looking at the doping profile, the actual doping profile is shown in figure D. Since we are using p-type silicon substrate, thus Na is constant. At the region where we doped with n-type doping, Nd is higher than Na. Thus, this region is a compensated semiconductor. The effective doping concentration is then N'D equal to Nd minus Na, as what we have learned in chapter 2. At the region with the p-type doping, the concentration is equal to Na. The point where the n-type region and p-type region is at the boundary is called the metallurgical junction. Here, Nd is equal to Na. We then apply the step junction approximation assumption to this model, in which the substrate doping is taken as the baseline. Thus, the graph in B can be drawn. The step junction approximations are listed here. We have seen that we have taken the doping profile as a step function. From the fabrication process, we have understood that the PN junction is made of compensated semiconductor. Thus, these equations are valid. But in the calculations that we are going to do during quantitative analysis, we will assume that all given values are n prime A and n prime D, meaning that we will use the values as it is. All impurities are ionized. Thus, the electron concentration at n site and n node is equal to n prime D. Hole's concentration at p site, pp node, is equal to n prime A. For a general p-n junction, non-degenerate semiconductors are used. Thus, impurity-induced band gap narrowing effects are neglected. But for a one-sided junction, which is made using an extremely high doped material, or we call it degenerate semiconductor, at the degenerated site, if it is an n-type, EF is overlapped with EC, and if it is at a p-type, EF is overlapped with EV. So that's all for the introduction of PN junction. PN junction is the simplest two-terminal device, which is also known as diode. Diode is a device that permits current to flow only in one direction, and generally PN junction is made of the same material, which is silicon. Finally, step junction approximation and assumptions are important for further discussion of PN junctions. I hope you don't keep the questions in your head just to yourself. Please ask me anything through our communication platforms. See you!